Hi, good morning, everybody. My name is Sami. I'm the Technical Program Manager at Facebook. Today with me, we have Wang and Shen from Hardware Engineering at Facebook. And together, we're going to present architecture of Minipack, the low-power switch that we announced yesterday. So here's the agenda of the talk today. We'll start with the Minipack hardware overview, followed by a deep dive of Minipack hardware from Wang, and then followed by a MiniLake hardware deep dive from Shen. Just for information, MiniLake is the microserver module that we developed as a control plane for Minipack. So Minipack is our next generation fabric switch, 128 port, each port is 100 gig. It uses cutting edge switch ASIC from Broadcom, which is Tomahawk 3. Supports mature optics, which is CWDM4, 100 gig. The box compared to backpack consumes less power, almost half power of that of backpack, and its height is about half. The backpack was about 8 RU when we introduced it, and Minipack is about 4 RU. So almost half of the space in terms of height it consumes, and in terms of power is almost half of the power. Currently, for the fully loaded optics, it consumes less than 1.4 kilowatt. So here's some of the basic components of Minipack systems. Starting from the top, we have switch mainboard, or we call it SMB, which has the basic switch, associated circuitry, thermal power, and all the things on a single board, and that is the main board. And then we have modular architecture, means that there are few cards in it. Starting from the top, we have system control module, which is basically a carrier card for a CPU module or the microserver module, which is MiniLake, to host it. And then we're introducing port interface modules, or PIM cards, like we say, and we're introducing two flavors of them. One is PIM16Q, which has 16 port QSFP 2800 gig each port. And we're also introducing PIM4DD, which has 4 QSFP 56 400 gig ports. Then we have fan control module, or we call it FCM. There is one board on the top and there is one board at the bottom. Fan control, following by fan control, we have power distribution system, which consists of horizontal bus bar supported by power distribution boards, PDB we'll call it, and there is one on the left and one on the right. Together they distribute power for all the components of the chassis. And then we have DOM FPGA, which is developed to facilitate movement of data from the optic modules in and out of the systems. So this is a high overview of Minipack chassis architecture. So chassis basically is an orthogonal direct design, which means that we have enough air space for the airflow to have a better thermal performance and efficiency of the system. Then we use CWDM4 optics, light, which runs up to 55 degrees centigrade. And in terms of electrical routing, we have shortened the route lengths to improve the loss insertion of the electrical signals. The architecture is FRU, which means a field replaceable modular architecture, where we have PIM cards and SCM cards which can be field replaceable. An interesting thing about this architecture is that tomorrow, if we choose to build our own PIM cards to fit our own architecture and usage, we can redesign, and we can design new PIM cards and customize the chassis to our needs. And finally, we have also the SCM board, which is full field replaceable, which hosts the microserver. So in terms of usage, like Alexei explained, the Minipack is designed to use all 3 levels of our fabric as a fabric switch, in a spine, as well as a fabric aggregator. And it supports multiple generations of top-of-the-rack switch in our fabric. So at this point, I will have Wang come in and take a deep dive on the Minipack architecture.
Thank you, Sami. Well, in the essence of time, I'm not going to wear this. Hello, everyone. So my name is Wang, and I'm a hardware engineer at Facebook Network Hardware Engineering. And so let's start from our current generation of fabric switches, which is Backpack. It is built from 12 Broadcom Tomahawk 3.2T switch chips on both line cards and fabric cards in a folded closed topology. And it supports 128 QSFP 28 CWDM4 modules. Going forward to Minipack, it has only one switch ASIC, which has been highlighted multiple times earlier. It is Broadcom Tomahawk 3. And as part of, a key element of our F16 strategy, it uses the same mature 100 gig CWDM4 optics, which are available in mass volume today. Tomahawk 3 chip natively uses 50 gig PAM4 SerDes interfaces, while the 100 gig CWDM4 optics uses NRZ 25 gig interface. So we use reverse gearbox chips to bridge between. Well, just like every generation of Facebook design switches, we have this concept of switch element. We have Tomahawk 3 switch ASIC and the BMC both are on the switch mainboard, while the microserver or MiniLake is on a switch control module. The reverse gearbox chips or the retimers on PIM16Q or PIM4DD. And this is a front view of Minipack with PIM16Q or 128 QSFP ports. As you can see, both the PIM and the SCM are vertically oriented. So why do we do vertical orientation? It is a very important design decision that the team made to simplify the chassis design so that we have more space to play for the Tomahawk 3 switch chip and the switch mainboard, as well as enough space for all the orthogonal direct connectors. And it also gives us better granularity or finer granularity in terms of number of ports on each PIM16Q. However, there's drawback because it's not so easy to fit 8 vertically oriented QSFP ports in one column in a 4RU space. And there is also a fiber routing challenge because eventually you have to route your fiber to the left or right sides of your rack. And our mechanical engineer, Jimmy, and our cable teams came up great solutions for both. And here is a Minipack front view with PIM4DD or 32 QSFP DD ports. Well, this is a Minipack's rear view, and we have AC/DC PSUs and the fan trays as rear throughs. This picture gives you another view of both the front throughs and the rear throughs of Minipack. Like Sami said, Minipack is based on orthogonal direct architecture. Well, people usually think about it as the signal connections, the high-speed links, but power distribution is actually a very important part of any modular chassis design. And I want to show you this Minipack bus bar that distributes the 12-volt DC power from the AC/DC PSU to the SMB, the PIMs, and the SCM. When we started Minipack, we picked the Bell Power AC/DC off-the-shelf PSU, and it can work up to 230 volts AC. As you probably know, inside Facebook data centers, we distribute 277 volts AC to the open racks to save one stage out for utility transformers to improve efficiency. To be consistent and to enable Minipack to directly work off 277 volts AC, we worked with Delta to customer design another new AC/DC PSU for that purpose. And this table shows the Minipack power consumption with all 128 ports running at full 9 speed. Every QSFP port is populated with 3.5 watt electrical loopback modules in this test. As you can see, the power consumption changes a lot when the fan PWM goes up That's because the fan power consumption increases exponentially when the fan speed goes up. So one key design objective of the thermal is to keep the fans running as slow as possible and to consume as little airflow as possible. And our thermal engineer, John, spent a whole lot of effort on that. In the data center, not just power, the cool air is also a precious resource. So if you go to our booth, look at the real Minipack, you could see big heat sinks. And as you saw earlier, we have 8 rear fan trays. Actually, we don't have to use so big a heat sink or so many fans to cool these components, but that is the most efficient design in terms of airflow and power consumption. So in Minipack, we use the same fan tray, exact same fan tray as backpack. So our data centers can have fewer types of spare parts. PIM16Q supports all kinds, 40 gig, 100 gig, and up to 200 gig optics, while PIM4DD support 400 gig QSFP DD and 200 gig and 100 gig QSFP. So let's look at the components and some details on each circuit board. SMB switch mainboard has Tomahawk 3 switch chip, the BMC chip, and the 16-port out-of-band management switch, as well as the IOB FPGA. We will talk about that a little later. And this shows you the components on SMB. And if you go to our booth, you may not be able to see a lot of components because they are covered by the big heatsink. On PIM16Q, we have the reverse gearbox from Broadcom BCM81724, and it translates 250 gig PAM4 channels to 4 25 gig NRZ channels per 1 gig port. It also translates different FECs for PAM4, which is RS544, and the FEC the FEC for NRZ RS528. And there is a DOM FPGA on each PIM16Q. Oops. Here is a photo of PIM16Q. So on PIM16Q, the left column of ports support 40 gig, 100 gig, and 200 gig speeds, while the right column of ports supports 100 gig and 40 gig modes. PIM4DD is designed for 400 gig QSFP DD ports, so it does not have gearboxes. Instead, it has retimers, Broadcom BCM81328 to retime all the 50 gig PAM4 channels. And there is no FEC termination and regeneration required. There is also a DOM FPGA on each PIM4DD. And this is a photo of PIM4DD, as well as the heatsink. The system control module is really a carrier of the microserver MiniLake, which my colleague Hao will talk into more details about it. And this is a photo of SCM, and you can see the red-colored CPU module and the SODIMMs on it. So Minipack has a couple of fan control modules. It distributes 12-volt power to the fans, and there is a CPOD on each FCM. BMC talks to the CPOD to control the fan PWM, as well as reading back the fan tachometer information. If you look at our previous generation of switches, even starting from wedge, we have Silicon Labs CP2112 USB to I2C bridge for the CPU to access the I2C bus of the QSFP modules. But in Minipack, we can have up to 128 QSFP modules. And that is not a scalable solution to CPU to access each and every QSFP through this slow I2C bus. So we introduced IOB and DOM FPGAs to basically offload the CPU from direct I2C accesses to the QSFP modules. The DOM FPGA can periodically autonomously go out to each QSFP module and read back the digital optics monitoring information and store it in its internal RAM buffer. And the CPU can just read from the RAM buffer instead of direct I2C access. Another benefit with DOM FPGA is the BMC can read the optics temperature information from the FPGA buffer as well, and use that piece of information as for system fan control. So previously, as the I2C bus is only attached to the CPU, BMC did not have this piece of information. Specifically in Minipack, we also put the master MDIO master controllers inside the FPGA, so CPU can control and monitor the gearbox or retimer chips through the FPGAs. And this is a block diagram of IOB and DOM FPGAs. The IOB FPGA is essentially a PCI Express bridge from the CPU to the DOM FPGAs, and there is a proprietary interface, we call it SLPC, between these two FPGAs. We opened it up and put the specs inside the Minipack OCP spec. So any third party can design their own PIM cards with DOM FPGA and plug into Minipack and talk to the IOB FPGA. Okay, then I will hand this to my colleague Hao to talk about MiniLake. Thank you.
Thanks a lot for Shu's introduction. Hi, everyone. My name is Hao. So today, I'm going to give a little bit more introduction about the MiniLake in Minipack. Yeah, so basically, MiniLake is the modular microserver that used as a CPU head node in the Minipack. So currently, you will know this is a standard form factor, and the reason we want to build the MiniLake by ourselves comes from those three benefits we look at. One is we want to choose a compact solution that is not only fitting in the Minipack, but for our overall network gear solutions. Another one is we do have some modifications on the IOs, expansion of the IOs to provide more rich features, and also MiniLake will support the BIOS and the Open BMC features that is contributed by Facebook to OCP. So this table gives us a brief view of the configuration of the MiniLake. You can see the MiniLake will choose the 95mm by 125mm form factors. And also we choose the Broadwell DE 1527 CPUs, which is a 4-core. It's a low power consumption, and the feature is good enough for our network applications. For the DRAM side, we choose 2 DDR4 sodium slots, 32 GB. I will go to the IOs in the next slides because it's more comprehensive. So this is a block diagram of the MiniLake. You can see, except the Broadwell DE CPU and the SODIMMs, all the IOs is coming to the COM-E connectors, we follow the Type 7 COM-E connectors. In addition to the COM-E, we do have added more PCIe lanes to provide more features, in case you want to use it in the other purpose. And also, there is an embedded controller, which we call the Snowflake, so that we can use the Snowflake to communicate with the BMC on the system board. So this architecture, this Snowflake architecture, actually is exactly the same as the Facebook's Type 1 Yosemite servers. So basically, our software stack can be reused a little bit. So as a hardware guy, I'm very happy I always want to show the real PCBs there. You can see the whole PCB is a very compact design. You will have the CPU in the middle and the DRAM on the right. And also you can see like all the CPLDs and Snowflake microcontrollers put it on the side. That makes the board a very dense board. As a hardware guy, it's a little bit tricky to put everything there, but it's glad things like the benefit it brings us is it's a similar architecture as our Type 1 servers, so a lot of work we can reuse. Talking about the power consumption, so this is low power consumption CPU we choose. So you can see like for the whole Minipack design, actually the thermal thermal has been taking a lot of careful design and considerations. So for the computer SCM module is on the side of the box. It does not take a lot of airflow. So which means like this design, one is like we choose the SKUs that deliver the low power consumption that is good for this application. Two, it does not create any burdens to the thermal cooling. So overall, like you can see the power consumption of the whole Kami module microserver is less than 50 watt. So this is the mechanical drawing of our module. It follows the Kami spec completely, so it's fully compatible. And the thing is like for the heatsink, we do specify 14 millimeters of the height clearance so that you can put the proper heatsink in our system. That's the only thing you need to take care of. At the end of the presentation, I still want to remind people about where the MiniLake is so that once you go to the booth, you can easily find it. So here's the Minipack system. You can see all the PIM modules and SCM modules like have all the optics. The PIM module is on the SCM module actually is on the leftmost, which is here. You can see actually the MiniLake module is assembled on top of the SCM module, and the module labeled in the red rectangular box is the MiniLake itself. So welcome to check this in our booth. In the end, like we want to call some actions. We already contribute all the EE design files, ME design files, and the OCP specification of the whole Minipack system, including MiniLake, to the OCP. And also we want to give recognition to our ODM partners, EdgeCore for the Minipack system, and Quanta for the MiniLake. Thank you very much.
Thanks, you all. We actually have time for a couple of questions, but in the meantime, just if Sami and Shu, you can come up on stage. In the meantime, Alex, if you can start swapping and getting your laptop up so we don't lose time with the whole AV swap. Any questions for the hardware team about Minipack or MiniLake? Or for, I don't know if Alexi is still here, if you were here for the earlier presentation. If you have any questions, please step up. Can you use the mic or just speak up? Just ask your question.
Yeah, go ahead.
If you can repeat the question.
So the question is the thermal threshold or the highest temperature Minipack. Is that correct? Well, we tested up to 35 degrees Celsius and 6,000 feet altitude.
Other questions? Go ahead.
So do you have
Hello?
dual BIOS chips like you have in the other systems?
We do have the BIOS chip on the MiniLake system. And also, like, you could choose to use the second BIOS on the system board.
Okay, great.
Yeah.
Thank you.
I have two questions. One is your DOM FPGA. So the DOM FPGA will automatically detect the object plugged in, unplug, and also read all the object data. How about the diagnostic data like temperature, voltage, all these things? Are you going to periodically read and put in the FPGA registers? So that's the first question. The other question is about the gearbox MDIO pins. Do you route this to the, to the CPU, or you route to the Broadcom chip? Okay.
So the first, So the first question about the DOM FPGA. The CPU can set up the DOM FPGA in a way that which address space or QSFP address space it will periodically poll. And it does include, well, in our use case, it does include the voltage and the temperature and the optics power information. And regarding the second question, the MDL interface in this case is actually connected both to Tomahawk 3 as well as to the DOM FPGA, and there is a max. And essentially, the CPU can either go through Tomahawk 3 or go through the IOB/DOM FPGA.
Okay, is there a place to find the